No, yesterday we were talking about the validability of metals by solid state joining processes. So in solid state joining, you know that the primarily the deformation coupled with the diffusion and other metallurgical transformations that will be taking place, and these two three things primarily determine the joint performance. But the deformation as well as the metallic intimacy and the metallurgical transformation which will be taking place, that will depend upon the number of factors, and that's why we talked about the factors affecting the ease of joining by solid state joining processes. Okay, so here we have talked about the number of factors affecting availability or ease of joining of metals by solid state joining processes. If you change the approach, the ease of joining is affected significantly. That's what I talked earlier, like the procedure, the purpose, and the fabrication conditions are those bigger or higher level of factors which need to be considered while evaluating the validability or ease of joining of the metals. So in this connection, we have talked about the chemical properties. We have talked about the relevant physical properties and also the mechanical properties, particularly the yield strength and the elongation or the ductility. So there are certain metals which are each metal has its own stacking fault energy. Okay, so this is one of the metallurgical term, stacking fault energy. In short, it is written as SFE. So the metals having the low SFE, they show the very high strain hardening tendency. Which means for less deformation there is a significant increase in hardness, and these kind of tough metals, and this behavior you can understand easily from the stress strain diagram, where as soon as you go in the plastic zone, the curve shows the different curve can show beyond the yield point, can show the different trends. So it may go, one possibility is this, another possibility it can be like this, where increase is somewhat slow, or it can be further lower. So this slope indicates the rate at which the metal is getting work hardened or strain hardened during the deformation, during the plastic deformation. Okay, so the low, medium, and the high work hardening rate or the tendency. So work hardening exponent is basically used, strain hardening exponent is used to characterize this. So like aluminium has got very low work hardening tendency, while your other metals like the stainless steel, cobalt, they show the high work hardening tendency. So what happens, in solid state joining, what you need is that either micro or macro level deformation. This is the requirement to have the metallic intimacy and the close contact between the components to be joined. So by considering this requirement, in view of this requirement, since the deformation is, you can say, the prerequisite for this kind of joining, and therefore so the metals which are having the low work hardening tendency, they will allow the deformation without much resistance. means the metal at the surface is getting deformed and near the interface is getting deformed. It will be hardened but not much. So hardening will not be resisting the deformation significantly in case of the low work hardening metals. So it will allow the easy interfacial deformation and easy metallic intimacy, closeness, mechanical interlocking. All those benefits will be there, and the same will be experienced other side as well. So the low work hardening metals will allow the easy metallic intimacy under the identical conditions of the external pressure as compared to those which have the high work hardening tendency. High work hardening tendency means you apply little load beyond the yield point, and the metal, as soon as the metal gets deformed, it gets hardened and resists the further deformation. So you need much higher level of the stresses. So the point here is some of the metals will be getting work hardened very rapidly and they will resist the deformation. So they will resist the closeness, means the metallic intimacy will be reduced, and if it is reduced, your all diffusion or the metallurgical interactions which are expected for the metallic continuity by solid state joining, all that will be adversely affected. Okay, so the point here is very simple. Your increasing work hardening tendency will be reducing the deformation tendency, and that in turn will be increasing reducing the ease of joining. So ease of joining of the metal by solid state joining, that will be reduced with the increase of work hardening tendency. This is one aspect with regard to the metallic intimacy and the metallurgical continuity. This is just one aspect. Okay. Now, what is the significance and what is the gravity and what is the relative importance of this aspect? About that I will talk little later. So this is about the analyzing the role of the different the factors those will be contributing towards the joint performance. Okay. So apart from these chemical, physical and mechanical properties, the one work hardening, also work hardening tendency of the metal also affects the solid state, the ease of joining by solid state joining processes. So it is preferred that metal is having the low work hardening tendency, or those which have the low work hardening tendency can be joined easily using these processes as compared to their counterparts of the high work hardening tendencies. Okay. So then coupled with this is the, I hope you might have heard the word thermal softening. Thermal softening is about the way by which, or the change in the hardness, your strength or your ductility. How these characteristic mechanical properties are affected by the temperature variation, especially on the higher side. We are talking about the higher side because the story on the lower side is completely different. So sub-zero temperature behaviors are completely different than what we get at a higher temperature. So one simplest possible example here is most of the metals in general, if you take aluminium, it will show the tendency like this with the increase of temperature in terms of, like, say, sigma y. If you take mild steel, so mild steel at room temperature is of the higher strength, but it may again come down very rapidly. So this may be 100, this may be, say, 300. It will be coming down very rapidly. If you take further higher temperature metals, this may be taken for the longer higher temperatures, maybe around, say, 400 to 500 degrees centigrade, say, for austenitic stainless steel. If you take further higher, like, say, 800, it may be going like say HSS kind of thing, high seed steel, cast cobalt alloys. Then you have further higher like tungsten carbide or those PCBN which can withstand maybe 5000 or 1200 degrees centigrade. Above 800 even tungsten carbide starts decomposing. So the point here is and the same is true for your hardness. So the point here is the metals lose their strength, lose their hardness, and they tend to be more ductile and soft. These are, and there are multiple causes for this kind of change, which may be in form of metallurgy. This you can say the metallic weakening basically. With the rise of temperature, and other factors like initially at low temperatures there may be recovery, recrystallization, then grain growth, apart from the metallic weakening due to high temperature. At the high temperature, okay, so the accelerated creep and very and those factors which are governing the cross slip and the grain boundary sliding, all those can be contributing for easy deformation at a higher temperature. So metal tends to get softened. This is the simple point I want to make. So if the metal is getting softened very rapidly with a little rise in temperature, it is good, because softening of the metal due to the increased ductility and reduction in yield strength, that will be facilitating the deformation. So basically softening is facilitating the deformation, or if it is taking place, the interfacial deformation is facilitated due to the thermal softening. It's good for improved metallic intimacy or bonding. And if it is happening, then certainly your the joint is going to see all the metallurgical interactions and the diffusion, etc. They will be taking part very effectively in joining process, and the joint will be good. Okay, so this is the another aspect. What we talked earlier, the work hardening, which was resisting the deformation and making the metallic closeness and intimacy difficult. On the other hand, thermal softening is just opposite. So each metal shows the different kind of the hardening and the softening behavior, and that is why you may find a lot of difference in terms of the ease of joining by solid state joining techniques. Okay, so this is the another aspect. Now coming to the what we call the physical metallurgy. You see the role of physical metallurgy. It has a lot of dimensions. Maybe I can try to summarize some of the aspects. So with regard to the physical metallurgy, first of all we have to see what is the main metal strengthening mechanism which is to be joined. Main metal strengthening mechanism, or the based on which a given metal which is to be joined by solid state joining process has been strengthened. So for that, what you need to consider, you see solid solution strengthening, then grain refinement, precipitation hardening, then work hardening, then your transformation hardening, and dispersion hardening. Okay, so these are like say 5-6 the mechanisms which are primarily used for designing most of the alloys as well as the composite materials. And when the metals which are strengthened by the different mechanisms, they are subjected to the solid state joining, their responses will be different. What earlier I talked about was like response of the heat, but here it is not just the heat that will be involved in solid state, but both the combination of the deformation as well as the heat. So since the different processes will be involving the different degree of deformation, they will be generating the different amount of heat. So since these both these factors are process specific, okay, say in few processes it is high, maybe say ultrasonic or ultrasonic or your FSW. See, you can say in FSW your high heat generation, and the deformation is also significantly high. In ultrasonic, the deformation is very limited, and it is expected that heat generation is also low. But sometimes heat generation in this process also can be significantly high, although it is very localized at the interface. But that is not the case in case of FSW. Similarly, in explosive welding also, your explosive joining, your solid state, what you call the limited deformation as well as limited heat generation. So if you see the different processes, the different amount of the heat and different amount of the deformation that will be taking part in the joining process, or those will be imposed. The different amount of heat and the deformation will be imposed during the joining. So since each metal strengthening mechanisms respond differently to the deformation and to the heat, so each may have its own role in strengthening, in determining the strength of the joint. Okay, so the major thing here is to see this metal strengthening mechanisms and the way by which these are getting affected by the deformation and heat, which is again you can say the process specific. Okay, so now I will talk how these are going to be affected when you apply either less deformation or more deformation or heat. So one side what I will do is that let me deformation, and another side heat. The way by which particular mechanism, a metal strengthened by a particular mechanism will be affected. So the metal which is strengthened primarily by the solid state, solid solution strengthening, where the deformation and the grain refinement role of other mechanisms is limited. Okay, so as far as the heat is concerned, deformation, effect of the deformation will be low, effect of heat will also be low, because here is the strength is primarily being imparted through the presence of alloying elements in the matrix. So say alloying elements are going either as a solid solution or as an interstitial solid solution or substitutional, and their presence is not going to be much affected with the application of the heat or with the deformation. So the effect of the deformation or heat being applied during the solid state joining processes on the solid solution strengthening metals, that will be very marginal, very limited. Okay, then you have the grain refinement. When you if the grain refinement is the metal strengthening mechanisms, say you have particular grain size like this, say 10 micrometer or 5 micrometer, say in the beginning. Okay, so the deformation will be causing the elongation, and the aspect ratio may get modified. That is one thing. Second thing, if the deformation is very severe, then it can lead to the fracturing and refinement of the grains. So for the moderate deformation, there may be just the change in aspect ratio and the increase in length. Otherwise, it can lead to the refinement. Say, so the aspect ratio and the refinement, these are the two possibilities. So like say if the deformation is very severe, then you will find that a lot of fracturing of the constituents have taken place and it has got refined. On the other hand, if heat generation is also good enough, then deformation coupled with the heat, this can cause the dynamic recrystallization. Okay, dynamic recrystallization. Okay, so this will be leading to the development of the newer fresh grains or refined grains. So the refined new grains will be formed. Okay. In case of the precipitation hardening metals, deformation will be doing the same thing, but effect may be limited. You see, so the precipitation hardening metals, these also can get refined, but at the same time, when these precipitation hardening metals when are subjected to the application of the heat. Refined means if you earlier you had a precipitate of 5 micrometer or 2 micrometers, so these may get broken very badly, so these may not be detectable, and when the particle size or grain size is reduced significantly, then these will have tendency to get dissolved very easily under the effect of the heat. So that there is a possibility that all these precipitates can get dissolved. First they will get fractured and they will get dissolved, and this is what is termed as reversion. So this refinement may cause, you see, earlier you had say grain size of the 10 micrometer, and after this deformation you might get 2 micrometer average grain size. So theoretically, as per the Hall-Patch relationship, there should be improvement in strength, but since the metal strengthening mechanism here is the presence of the precipitates which are getting lost, getting dissolved, so you may lose your strength significantly. So on the relative importance of these changes, I will talk little later, because this has to be understood depending upon the strengthening mechanisms and the way by which heat and the pressure are being applied. The relative importance of the each mechanism or each change can vary significantly. It can be significantly different for the different application of the deformation and heat. So if you see in nutshell, here you are getting refinement, but at the same time your precipitates are getting lost. So the precipitation hardening metals, sometimes they lose their strength and hardness. So they so the joint interface tends to be weak as compared to the other metals like the work hardening metal or transformation hardening metals. So here what you got, grain in precipitation hardening you got refinement, but lost the precipitates got dissolved due to the application of the heat or rise in temperature. So you may lose lower strength as a combined effect. Okay, so your joint efficiency can be drastically reduced, say maybe 50%, 60% as compared to the base metal, because of these losses of the precipitates. Okay, coming to the work hardening. You know, if you take any work hardening metal and you deform, no, it is simply going to get increase of strength. It's good. Strength, hardness will be increased, although at the cost of ductility and toughness. It's fine. But on the other hand, if you see, you apply the heat, if the heat being generated is very marginal, then effect will be less. If the heat generated is significantly more, then there won't be any effect of the work hardening. So work hardening effect is being imparted through the development or generation of the newer dislocations, and when the heat applied is significantly high, then this will be causing the recovery and the recrystallization. And so you are getting in one side, you are gaining in one side, but you are losing another side. So depending upon the process, whether it is the deformation that is dominating or the heat is dominating, that will determine in totality the performance of the joint. Okay, so work deformation will be facilitating the increase of strength. On the other hand, heat will be compromising. Okay, so if you can realize the deformation without inducing much of the heat or by controlling the rise of temperature through the external forced cooling, then it's good. You can improve the strength. So next is the transformation hardening. Like transformation hardening is shown by, like, wherever there is a change of phase due to the either deformation or due to the high increase of temperature followed by cooling at different rates. Okay, so there are 2 or 3 examples of this kind. The most common one is ferrous systems, iron, carbon, or it's a family. There are huge category of metal like cast iron, your wrought iron, and then steels, stainless steel, and so many. So all these are of the iron family. All these, most of these show the tendency, except very low carbon steels, they do not show, but they also show, like steel having 0.2% carbon steel can also show little hardening in laser welding. So the point here is, most of these iron family systems, and there is one more, copper, tungsten, Ly, they also show the transformation hardening, where earlier you had one phase, and when it is subjected to the rapid heating or holding at high temperature for some time followed by the cooling at different rates, you find a lot of change in phases, and whenever this change in phase will be taking place, it may cause increase or decrease in the strength and hardness. So transformation hardening metals are like, mostly these are hard naval steels, and like say even the copper alloys. This can be observed. Even some of the titanium alloys are of that kind. So the point here is, if due to the application of deformation or due to the application of the heat, if the metal is experiencing the change in phase, then that change in phase can lead to the change in strength and hardness. So the way by which this change in phase and the change in properties taking place, that will determine whether there will be increase of strength or decrease of strength. Okay, so I'll give one example to substantiate this what I have just said. Okay, so if you take any hardenable steel, okay, any hardenable steel, say steel 0.3% carbon steel, okay, and likewise there are a number of things. So when you apply either deformation or heat or both, so there is every possibility that you will get the hardening, means there will be Martensite transformation, okay, or there will be deformation assisted transformation. This is another thing, deformation assisted transformation. So these are the 2 different things I will take up differently. So coming back to the same, so what I said, you apply deformation. So in some of the metals, like ferrous metals, like maybe high manganese steel or some high nickel steels, Hadfield steel. Now, all these steels, when they are subjected to the deformation, so the austenite present in these steels transforms into the martensite. So this transformation, even at a low temperature, assisted by the deformation. So what we say, it is deformation assisted transformation hardening. This is very interesting. So Hadfield steel, when they are used, such kind of the steels are used to make the components which will be subjected to the shock loading or a higher level of the stresses during the service. So the surface layers will be undergoing the deformation as well as the transformation assisted or deformation assisted transformation, and that in turn will be leading to the increased hardness and strength. Increased strength and hardness of the component surfaces during the service in turn will be leading to the improved performance. So that is good. So those joining processes, let me use the another one, those joining processes, where the deformation at the interface is involved. So with a little or more heat generation, in both the cases you will see transformation hardening, either it is just the deformation assisted or contributed by the heat. If that is in both the cases, if it is causing the transformation of the soft phases to the hard phases, then it is going to increase the strength and hardness of the joint. So what you can find, how can you verify? You just plot the hardness distribution at any location in the weld joint. Say these are the dots where you are taking the hardness distribution, and see that hardness distribution, it is constant, but as soon as you come across the weld, then there is an increase in hardness, then again it comes down like this. So this is suggesting the base metal hardness, and whenever there is a change, gradual change, rise and then down. So this increase in strength and hardness is contributed to your transformation of soft phases to the hard phases, and that has led to the increased strength and hardness. This transformation may be of the different type, like your perlite or benite, or martensite, ferrite and perlite, they have got transformed into the benite or the martensite. Okay, so this is what you can say as the way by which the transformation hardening metals can respond to the deformation as well as heat. In most of the cases, they show hardening, and that is why whenever the steel or the copper alloys, they are joined using solid state joining process, invariably they show the joint interface is harder and stronger than the base metal. Okay, especially in these autogenous solid state joining processes, unless we use some kind of the interlayer. Interlayer will be facilitating the metallurgical compatibility, but may be weakening also at the same time. Coming to the last dispersion hardening mechanism. In dispersion hardening mechanism, it is very simple. Like you have metals where you have in matrix you have finely dispersed hard particles or soft particles as per the case. When these are subjected to the solid state joining, application of the deformation and the heat. So don't expect much for the heat, that heat will be causing damage to these reinforcing agent unless the temperature rises more. If the temperature rise is very high, then the reinforcing agents can interact with metallurgically with the metal matrix, and that can compromise. On the other hand, if the deformation is severe in this vicinity, then it can cause the fracturing of the reinforced agent, and fracturing will be leading to the refinement. That's one. The second possibility is that there is a possibility of the decohesion between the particles and the matrix. So there is a possibility of decohesion as well as poor bonding between the particles and the matrix, so which can weaken the material. So if this is dominating, then it can weaken, and if the refinement is dominating, then you can say there will be improvement. It depends. Okay. It is expected that the dispersion hardened metals will not be much affected by the solid state joining processes. Now coming back to the our earlier positioning, it is important actually. This will be very helpful. Solid is solution strengthening. Then coming to the what it was, grain refinement, precipitation hardening, work hardening, transformation hardening, and dispersion hardening. Okay, so now so first thing you have to understand, you take any commercial alloy or any commercial metal, that will not be having its properties just because of one mechanism. The properties of any commercial metal will be affected by more than one mechanisms. Okay, so although relative importance of other mechanisms may be marginal, say you know that a simple carbon steel system, they gain strength from the interstitial solid solution of iron and carbon, right? But you also know that if the refinement is taking place, then it increases the strength, say from 350 to 400 MPa. So there is always change in the properties. Okay, so this is one. Steel may also have some effect of the work hardening. So not just the solid solution is strengthening and the grain refinement, it may also have some effect of the work hardening. So work hardening is contributing, say from 400 to say 440 MPa. Okay, so the main strength it was gaining from the solid solution strengthening, then marginal increase took place from the grain refinement, then further minor increase took place from the work hardening. So there is a possibility that most of the strength, say 70% is coming from one mechanism, and say the second mechanism is contributing 10%, and third mechanism is contributing 20%, right? So whenever you now have the favorable conditions, or whenever you have now the conditions of heat and deformation during the joining, then what will be happening? Due to the heat, your grain refinement effect can get lost. Okay, because the grain coarsening will be happening. Because of the heat, you may lose your work hardening effect. Okay, that is the 20% that you are gaining from the, but at the same time the deformation can lead to the refinement, and deformation can also cause the work hardening. So it is the relative importance of these two process linked factors, that is heat and the deformation. If the heat is dominating or if the deformation is dominating, accordingly it will determine if the grain refinement effect will be lost or it will be gaining, or if the work hardening effect will be lost or it will be gaining. So these are the subjects of the analysis, or these are the things of analysis. Okay, so if you how can I go back? Let's see. Yeah, so here if you see, if I plot just a kind of a joint developed by the solid state joining process like this, say FSW kind of thing. Okay, so here you may find the solid state joining process, it is expected that with the moderate heat and moderate deformation, there may not be any major change like this. But if the deformation is dominating, then the change will be like this. If the heat is dominating, you may find that there is a little dip also. Okay, So when the deformation is dominating, you get this trend. When heat is dominating, you get this trend. And if it is moderate, there is a marginal change in the properties. Okay, this is just one side. So the point here is the relative importance of the things can change significantly. Relative importance of these which mechanism is contributing how much, and how much heat is being generated and the deformation is being induced during the solid state processes, that will be determining the performance of the joint eventually. Say the grain refinement. Here you may find, okay, your base metal is of just 5 micrometer both the side, right? You apply heat and the deformation. So if the grains are getting refined due to the deformation, or if the grains are getting coarsened due to the heat, so that will dictate what will be the performance. So if draw the hardness distribution curve, if this is the only primary mechanism, then you will find due to the grain refinement there will be increase, and if due to the coarsening is dominating, then there will be decrease. So you have to quantify, you have to analyze all this. In precipitation hardening, you see typically what we get, your precipitates are usually lost, and that is the main thing. So sometimes despite of refinement, you get the drop in hardness joint. Okay, and if the precipitates have got lost, invariably we get a dip like this. So your strength is getting lost in the weld zone. So failure will be occurring from the weld zone only, not from the base metal or the heat affected zone. So in this case, because your precipitates have lost. On the other hand, if you talk of the work hardening kind of thing, metal joint primarily by the deformation, not by the heat, then you will notice that it is increasing the hardness at the joint interface. And if the heat is dominating, then certainly you will get the reverse trend in the work hardening metals, because the application of heat will be causing huge reversion and the recrystallization. So that will be leading to the loss of all the hardness, whatever you had gained from the work hardening of the metal. Transformation hardening metals invariably show the increased hardness and strength. That's very common, because both deformation and your heat application in transformation hardening metals, this causes the hardening of the things, and that's why invariably you get a lot of change. So initially at room temperature you may have 200 HV, but here you may get 400 or even 500 HV. So this is contributed to this transformation hardening metals. And about this dispersion hardening I have already talked. So this is about, like, you have to analyze a given metal is strengthened by which main mechanism, and what are the other mechanisms, and what is the contribution of other mechanisms in strength of the given metal. And based on the extent of heat being applied, extent of the deformation being induced during the solid state joining, your the final joint performance will be determined. You know why I am saying this? Because in some of the processes you will see the scale of the deformation is huge, maybe 5 mm, 10 mm of the volume of the metal deformed and induced, say, the strain of 1000 units. On the other hand, say micro deformation is taking place in explosive magnetic pulse as well as your ultrasonic welding. So in those cases the extent of deformation may be very limited, say just 10 or 15 or 20. So there is a lot of difference in the kind of heat which is being generated and the strain which is induced during the solid state joining. Okay, so this was about what the role of the metal strengthening mechanisms and ease of joining. What else I wanted to share? I think that's all about the role of the metal strengthening mechanisms and the solid state joining.